Okay. Great. So then, well, welcome everybody. Thanks to the program chairs for the invitation. As have been introduced, I'm Alessandro Barenghi from Politecnico di Milano, and today I will be presenting our point of view on the joint optimization of speed and security when designing code-based cryptosystems with code families which rely on iterative decoding strategies. In particular, I'll be picking the case of LEDAcrypt. Why? Because, well, because I'm a member of the LEDAcrypt team, and essentially, as Shai did, the first thing I want to do is to, well, acknowledge the work. I'm not doing this alone, luckily, and the LEDAcrypt team is responsible for the insight I got in this now 2 years and something long journey in code-based cryptosystem design. So the team is listed here in strict lexicographic order, increasing order, and well, it's been a bunch. I hope to be able to provide some of the insights we got and to get obviously valid feedback for that. Okay, without further ado, what is the common point when you're doing design trade-offs in engineering cryptography? Well, you typically have two constraints. One is security. You should design something to be secure up to a given point. And the other is that it should be as efficient as it is possible. And typically this space security trade-off or computation security trade-off takes place in every cipher design, symmetric, asymmetric, whatever. It's always arguing against, say, key size versus security margin, which is probably the most emblematic trade-off in space versus security. And the computation time versus security stems directly from the fact that the time complexity cannot be smaller than the space complexity. Hence, sure thing, if you have a compromise between space and security, you also have a compromise between time and security. So what's the usual approach? You set your own wishes, security desiderata, and then design the system to be as fast as possible within those limits. The goal of my keynote is to provide an overview on a design strategy and which are the trade-offs, how to design when you're designing a code-based cryptosystem and you want to pick sparse parity check metrics codes. Usually they go in the literature by the name of QC-LDPC, MDPC, depending on how dense is the parity check metrics, because if you look at them from the decoding capability point of view, they have different properties. The point is here the density will be seeing that it's a security parameter. So my personal view is that what drives the density itself, the choice of the density itself, is the security bar, and that's essentially it. So I'll use QC-LDPC, MDPC because, well, from a security point of view, they are sparse parity check metric codes where I decide how sparse by security constraints. What are the design challenges? Well, the typical design challenge in a cryptosystem involves the fact that you have a parameter, which is typically the key size, or I don't know, the size of the algebraic group on which you're working, which gives you the security margin and has a direct relation with the computing speed. In these cryptosystems, one of the main challenges is that the parameter space is not monodimensional. We'll be seeing that we have multiple parameters and they all influence the security in some way or another, up to the point that there are security equivalent choices for the parameters, and picking the best one is not immediately evident. The other two things relate to the fact that QC-LDPC and MDPCs, as Shai quite well clarified, are affected by non-negligible decoding failure rates if you use iterative decoding strategies. Now, one would be tempted to think to the decoding failure rate as just a functional issue. Okay, sometimes it doesn't decrypt. Okay, I'll send it again. But as we have seen, the DFR is crucial if you want to achieve security against active attackers. And there are two challenges relative to this. The first one is that the definition of the delta correctness, which is the measure of the correctness of an asymmetric encryption scheme used in the most common IND-CCA2 constructions, is given a certain way, which is delta correctness. And this way of defining the probability of failure is not the same way you have in common coding theory when you consider the decoding failure rate of the underlying code. This in turn means that we have somehow to match the worlds to get the benefits of these constructions. And then the fact that the decoder has a high DFR is a security concern, not just because the proofs don't work, but because there are active attacks exploiting a very high DFR. So we need somehow to cope with this, to find a way to cope in an engineering way with this. So without further ado, what's the object of the game? Well, QC-LDPC codes are chosen typically in the McAleese and LEDAcrypt systems, or at least I'll be dealing with these in this talk, as the secret code with efficient decoding, which is required to build the crypto system itself. Why pick them? Well, because since they are quasi-cyclic codes, they have very compact representations. Essentially, you can represent the whole parity check matrix with just its first row, which cuts down the space required to store it by, well, quite a lot, typically. They have a good fast decoder via the common iterative decoding strategies, and the code itself has no other structure other than the sparsity and the quasi-cyclicity, because it's randomly picked parity checks along the code word itself. So it's really devoid of any structure as much as possible, save for sparsity and quasi-cyclicity. And at the best of our current knowledge, the quasi-cyclicity only gives you a polynomial speedup in attacks, as opposed to some algebraic codes, which, as for instance Reed Solomon, which suffer from the fact of being used in a quasi-cyclic variant to build crypto systems. Apparently, this has no impact on sparse parity check matrix codes at all. So they are a nice candidate because we can use quasi-cyclicity. I'll be talking from now on about an iterative crypto scheme. All the design criterion I'm stating do apply to McAleese with the proper renaming of the parts. So just for the sake of clarity, I'll stick to the iterator. Okay, so a couple of definitions just to nail the letters. Essentially, I'll be talking about a code C, a QC-LDPC or MDPC code C, which is representable with a quasi-cyclic binary parity check matrix H, which is 1 times n tiling of circulant binary matrices of size P. So the row weight of the matrix is n0 V, and the column weight is obviously V because it's tiling of circulant blocks. And this is 1 block high. The code length is just n0 times P, the size of the matrix, and the code dimension is n0 minus 1 over P. So I'm picking the particular case where the code rate is always n0 minus 1 over n0. Now, T will indicate the number of errors that I'm expecting the decoding strategy to be able to correct with an acceptable probability. Unacceptable means extremely high probability of correction. Since iterative decoding strategies are not rigid radius decoding strategies, I'm just expecting that the failures occur very few and very far apart. And I'll call the DFR, the decoding failure rate for a given code, so for a given H, and a given decoder, because the DFR changes with your decoding strategy, the probability that given a syndrome coming from an error with Hamming weight T, the decoder fails in decoding it when acting on the matrix H and the syndrome given. So this is averaged over all the possible errors of weight T, in essence, and given for a single code. Okay, let's start with tackling the challenges. What was our take on the fact that we have to explore a multidimensional parameter space when designing? Well, first of all, what are the constraints on this exploration? Well, the security requirements for these codes involve the fact that I have to resist the common message recovery attack, which is done assuming that the parity check matrix is random, quasi-cyclic and randomly picked, and is done via information set decoding, which is a class of efficient algorithms in the sense that they are still exponential time, but they quite cut down the exponent for guessing where the errors are. The key idea is that in information set decoding, instead of guessing the error positions, you guess the error-free positions and apply a lot of very nice solutions to go faster than brute force. Well, I want the message, the error vector, to be dense enough to have a high enough weight to prevent these attacks. Then I have to prevent key recovery attacks, which are typically done, again, via information set decoding. Why? Because they exploit the fact that the code words of my code, of my secret code, are very sparse. So doing code word recovery via ISD hits the sweet spot. Well, it's still practically unfeasible, but it's the currently weakest spot to find the private key given the public key. I'm trying to find low weight code words. So again, it's information set decoding. This time, the figure of merit is the number of parity checks in a word. Essentially, with extremely high probability, it corresponds to the row weight of H. And I have to provide, one way or another, a sufficiently low DFR. So for lambda bit security level, AES 128 equivalent means lambda 128, the DFR should be below or equal to 2 to the minus lambda. So 2 to the minus 128, which is a stringent requirement, obviously. On the other hand, I have efficiency pooling because I have my public key, which is essentially n0 minus 1 times p bits if I use a systematic representation of the public key, which I do because it's efficient. And my ciphertext will be p bits long. So the shorter, the smaller the value of p, the better, because the shorter my public key and ciphertext will be. My decoding strategies, the ones that we will be tackling, are all polynomials and have a complexity which is substantially n0p times n0v times the number of iteration the iterative decoder does. So pick a shorter code length is n0p, and you get faster decoding. Pick a less dense code, pick n0v smaller, and you get faster decoding at a cost. Or cut down the number of iteration and you get faster decoding, unsurprisingly. And then obviously the entire arithmetic of circulant matrices is isomorphic to the one of polynomials modulo xp plus 1 over the appropriate field of the coefficients. So cut down on p and you get faster arithmetics. Note that one way to cut down on p while keeping the same code length is increasing n, but this increases the number of arithmetic operations I have to do, because for instance, the number of blocks in the parity check matrix increase, and that leads to more multiplications in the scheme, for instance. So to have a pictographical representation of who's pulling in which direction, we have our security requirements on top, which mostly pull for us to raise the parameter values, save for the DFR, which to be low enough would like to reduce the number of errors I want to correct while keeping the rest the same. And our efficiency desiderata are willing to lower our 3 code parameters. So this creates effectively a constrained optimization problem, which is hard to solve in a closed form, essentially because, well, the finite regime, also syntactic regime estimation for ISD complexities are not trivial. And so finding a single closed form solution for the optimal parameter set is a challenge. And then again, I neglected in the previous slides the fact that I also have to pick the code rate, that is n0 in my case. Now, for the code rate, the main point is it's hard to assess the constant term speedups and slowdowns given by changing n in the complexities of the algorithms. So the best we could do is pick a set of n0 values, implement the whole thing, get concrete data on all the n0 values, and then pick the optimal code rate when all said and done for a set of optimal PVT combinations. To find PVNT, we went for a fixed point solver because essentially constraints are, as I said, a bit too hard to solve in closed form solution. And fixed point solutions are not that slow in this case. I mean, they converge in 2 iterations, so hey, it's acceptable. Essentially, we assess the effort of doing ISD by finite regime ISD complexity computations. It's just take the formulas and do the math efficiently. We'll need to assess the decoder DFR in a trustworthy manner, and this is challenge 3, which we'll be dealing afterwards. One noteworthy point is that in this case, picking which decoder is security critical. Why? Because it influences the DFR. So while before it was just an implementation issue, is it faster, slower, whatever? Now this binding between DFR and security makes the choice of the decoder security critical. And also the difficulty of bounding the DFR also depends on the decoder strategy. For a very silly decoder strategy, which never corrects, well, the DFR is easy to derive. It's obviously 1. So this is an extreme example, obviously. But then again, picking a decoder which is easier to model in terms of DFR also helps in the design. Okay, so let's start by getting one thing out of the way, which is reconciling the correctness definition for the constructions and the coding theory guys' correctness definition, which is DFR. What came out during the NIST competition and was highlighted by Dan Bernstein in an observation on the mailing list was that the construction by Hofheinz and others in 2017 allows you to build an IND-CCA KEM, assuming you have a one-way CPA secure scheme, which is delta correct, which means it fails with less than delta probability under a given definition of that probability. The point is that delta correctness definition does not match the same failure concept of the DFR. So if you want an IND-CCA2 crypto scheme using the construction by HHK, you either change the proof and get a way to rebuild it or modify the construction itself, or you need to find a way to exploit the DFR information you have and fit into that scheme. Now, one quick note, as also Shaya underlined, the failures are not an issue only for IND-CCA2 scenarios, they are also a practical issue if they are too high. Targeting one failure in 10 to the minus 7 is not bad, but from some direct exchange with site reliability engineer in Google, if you want to target extremely reliable systems, 6 nines reliable systems, one failure in 10 millions cuts down your downtime budget by 10%, which is an appreciable portion. I'm not saying it's all of it, good Lord, no, but it's not negligible. And I was advised to target something like one failure in 10 to the 9 attempts, which is less than a 1 per 1,000 impact on a 6 nines availability system. So even with the most stringent requirements, 10 to the minus 9 in expected DFR is a good point to shoot at, probably. From my point of view, at least. Okay, so how do we match the two things which are not going according to plan? Delta correctness and DFR. Well, first of all, how are they defined? Delta correctness says that it's the probability that an adversary induces a decryption failure, taken as the maximum over all the plaintexts and the average over all the key pairs of the scheme. And this delta should be lower than 2 to the minus lambda for the construction by HHK to provide IND-CCA2. Now, the DFR typically given is for a given code, and it's averaged over all the possible plaintexts, that in that case are the errors. This means that the IND-CCA2 attacker, if he can choose freely the error pattern, the plaintext, he may swing the failure rate towards something higher than average. And since the delta correctness considers the most favorable scenario to him, the maximum overall plaintexts, this may yield a mismatch. This was pointed out, as I said, by DJB back then in 2009. We before provided a construction which essentially randomized the generation of the error and provided a way to check that it was randomly generated. And what we did lately was optimize the construction for efficiency, remove and redesign so that it's a slightly bit faster, and provide a clearer rationale for it. That is, in gray, you're seeing the HHK scheme as it stands, no modifications. The non-boxed part is what we added, and it's the part which generates the error message randomly using the output of an extendable output function, shake in particular, which is NIST standard. The idea is that if the attacker wants to choose the error vector E, This can be proven to be computationally equivalent to finding a pre-image for the XOF, which is pre-image resistant as it's essentially built on a hash. So the attacker is not able to pick E, he's forced to pick it as the output of a hash, which is random, unless he's able to invert shake, which to the best of our current knowledge is not feasible. Okay, so we're still using our good HHK and patch it at the end. Decoding design challenges. Now, as I said, there's no magic bullet which gives you a decoder agnostic formula for the exact DFR, because for iterative decoders, there's no way to do this with a decoder agnostic strategy. And even providing a decoder specific formula for the exact DFR for non-trivial decoders is still quite an open problem. You can do numerical simulations, obviously. You just decode a ton of errors and count how many times they fail, which will push you for good DFRs. I mean, 2 to the minus 30, 10 to the minus 9, it's still simulatable. You need a couple of CPUs, but it's doable. So for ephemeral use, it's more than fine to simulate. It takes quite some computation time, but you know, if you have the iron, go ahead. Our approach was different. We went for a worst case model for the DFR or very specific decoders, and we simplified the decoder design as much as possible, so to allow a modeling of the DFR which leaves little to the imagination, essentially. And obviously, Shai stressed this a lot, I won't nail the same hammer much again, a fixed number of iterations is a must. Leakage via time channel is worse than decoding failure leakage because it's leaking how many iterations you're taking, not just that 7 or whatever you did was not enough. So fixed number of iterations in an iterative decoder is the criteria. What did we do? We assumed a priori a fixed number of iterations, and that's it. Okay. How do we design our decoder? Essentially, we start from an error vector estimate, which is null at line 1 in this algorithm. We apply a number of in-place iterations of the decoder, which is iter max in, then a number of out-of-place iterations of the decoder, which is imax out, and then return whatever the error estimate at the end of the procedure is, and whether or not the syndrome value is 0. That means that I successfully decoded my error vector. Notice that there are 2 early exits to ifs at line 3 and 7, which can be blissfully omitted in the constant time implementation as they do not alter the correctness of the decoder. They just make it faster if you don't care about constant time implementations, which in case of ephemeral keys could be argued they are not strictly speaking necessary, as you leak an information which is too little with respect to the information contained in the key itself. And so in this case, it's arguable that you can keep them for CPA. But for CCA, well, forget about line 3 and 7 at all, and that's it. Okay. Which assumptions did we go at making to provide a model of the decoder iteration? Well, first of all, we assumed that during the decoder iteration, you're estimating how many parity equation checks are failing on a given position of your error estimate. So the UPC are the unsatisfied parity checks for the jth position in the error. If these are above a given threshold, you change your estimate of the error bit because it's likely wrong with respect to the actual error. So our idea is that the distribution of the probability of the UPCs does not depend on the position in the error. This makes sense from our standpoint because the error vector and the parity check matrix are chosen independently and randomly drawn independently. So in this sense, there shouldn't be preferred position if I go over averaging over all the errors. So this feels like reasonable to us to have the fact that the UPC distribution, assuming over all the possible errors, is independent of which bit I'm considering. Then the differences between my initial error estimate, which is 0, and the current estimate I'm looking at, and the error vector to be estimated, are assumed to be random. This is trivially true for the first iteration, where I start from a 0 estimate and a randomly picked error, But for iterations after the first one of the decoder, this is a concrete assumption, meaning that it's not a perfect fit of reality. But for the first decoder iteration, this is a perfect fit because the error vector is random. So its discrepancies from a zero vector are random. And we also assume that the rows of the parity check metrics are randomly picked. This is quite well established in the decoding theory history. I mean, the first one making this assumption was Gallagher back then in 1963. And one of the most recent papers doing this for estimating DFR is by Jean-Pierre Tillich in 2008 at ISIT. So we just picked this assumption because it's quite well accepted in the community, essentially. Well, reality check. We're engineers after all. We have a model. Does it fit reality? A model is only as good as it fits correctly reality, at least. What can we do? Well, clearly we cannot simulate the DFR down to the pits of 2 to the minus 128. But what we did was simulate for 1 billion decoding per data point, a single out of place iteration and a single in place iteration of the decoder. And what you're seeing is the out of place estimate in a solid line versus the numerical simulation. And in the other slide, the two estimates of worst case and average case for the decoder in place, which uses a randomized evaluation order for the UPCs, and the corresponding numerical simulation, up to 10 to the minus 8 in evaluated DFR. We stopped the simulations after reaching either 100 errors or 10 to the 9 decoded messages and plotted the thing down to the 10 to the minus 8 for confidence reasons. And as you can see, the estimate is not too shabby, I would say. So what did we do in designing the decoder? Well, we went for a 2-iteration decoder, hard limit on the iteration. So the assumptions we made are only for the first iterations of the decoders, and which is the case where the assumption on the discrepancies distribution from estimated error and actual error is essentially true. So one of the assumptions is not even necessary in this case. For the second iteration, we took a result which is a hard bound on the number of errors which can be corrected with certainty by our decoding approaches, and said that, okay, if our discrepancy distribution after an iteration exceeds the errors, the decoder will fail. This is clearly conservative because if my decoder corrects with certainty T-bar errors, it will likely correct with, well, at least once in a while T+1 errors. But this hard, quite conservative observation says that our estimates on the DFR on the second iteration are conservative with respect to an exact bound which relies on no assumptions, further strengthening our worst case analysis of the DFR of the decoder. So we're left with, what should I use? In place, out of place, a bit of it or a bit and a bit. I have 2 iterations. I can do 2 in place, 2 out of place, 1 and 1. What do I pick? Well, in-place decoders do correct better when you pick the same code parameters. They have a better DFR, so you can shorten the code slightly, but they are not parallelizable from an implementer point of view. And this is quite an issue because, well, because out-of-place decoders have a massive parallelism. They're essentially fully data parallel within an iteration. And this means that you get a parallelism factor degree, whatever you want to call it, of exactly the code length. This provides, as you can see in this experimental evaluation, about a decade in advantage in running time. So it's about 10x with respect to even a single in-place iteration, even taking into account the fact that I can shorten the codes to get the same DFR. So we went with the fully out of place strategy because, hey, it's faster. Okay, so what did we do? This is a quick recap as I'm going to conclude on the design strategies. For IND-CCA2 primitives, we pick a desired security level and our figure of merit to be optimized, whether it's decoding speed, bandwidth, or some joint metric, which has been rather popular, which is clock cycle plus bytes times 1,000, which takes into account somehow how much data you're sending and how much time you're taking to process it. Well, solve at fixed point for the desired parameters, PV and T, run the tests for different rates, and pick the best code rate depending on your figure of merit. While for IND-CPA primitives, well, the idea is that you still pick your desired figure of merit, whether it's speed, bandwidth, or joint speed and bandwidth, and then solve again at fixed point for the desired parameters PV and T, this time taking an underestimation of the DFR. That is, you aim for a higher DFR in this sense for a given set of rates, and then experimentally test whether you have the DFR you desire, raising P until it's numerically confirmed to be enough. That is, you aim for, I don't know, something like 5 10 to the minus 8 in DFR, and you want to have 10 to the minus 9, and then you gradually raise P until you get there. Takes a bit of experiments, typically 2 or 3 with our estimation, but then again, in this case, the DFR is guaranteed by the experimentation, so you know that it's going to be 10 to the minus 9 with the confidence you have in the experiments. And then, once you have all the parameters, benchmark the speed of the cryptosystems with the given parameters, pick N0 and go with the N0 you like. So just concluding quickly, what we have here is a set of results for LEDAcrypt-KEM for IND-CCA2 parameters, so tackling a DFR which is 2 to the minus security level, that is 128, 192, 256 for the 3 categories. And the very quick bottom line is that we're able to get a complete KEM in slightly less than a millisecond. That's 3,100 kilocycles on this desktop, on this simple desktop, with an AVX2 optimized implementation. We targeted AVX2 because it's the reference platform provided by NIST in the sense as the one we should optimize for. So we went with that essentially. And the transmitted data are about 2 kilobytes in ciphertext sent from one way to the other. What we ended up in picking for IND-CCA parameters is mostly code rate 3/4, that is N04. That is because it saves in transmitted data, so the combined metric, data plus computing speed, it's either N04 or 3, while the computation speed alone would suggest N03 for the first security level and 2 in the other cases. Same thing, same overview for IND-CPA primitives. What we get here is an entire IND-CPA KEM with ephemeral QUs, that is, key generation slightly less than 2 million cycles in speed for security level 1. And we send a little bit more data than the IND-CCA version, as in this case you also have to send the public key along with the ciphertext, because you have to send the ephemeral public key every single time. And that's kind of key exchange. While with long-term keys, the key sending is essentially amortized over all the interactions you have, and the only main concern you may have is whether the key fits in the device or not. Since our keys are always less than 10 kilobytes, this is usually not a problem, even for microcontrollers. Okay, so in this case, again, the rate choice changes depending on your metric. Computation speed this time is privileged by having higher rates, while just raw transmitted data is privileged by having lower rates among our choices. Okay, with this I do conclude, and here you have the link to the current specification of LEDAcrypt, which contains far more details on all the procedures than I could possibly hope to provide you in this keynote speech. Thanks again.